Hello everyone, this is Anu Agrawal here. Today I'm gonna tell you about structure of normal operators, which is a part of quadratic form. So first we should know that what is normal operators. A normal operators on a complex Hilbert space H is a continuous linear operator n from H to H that commutes with its Hermitian adjoint n star, that is n into n star is equal to n star into n. There are some points regarding normal operators. The first is normal operators are important because the spectral theorem holds for them. A normal matrix is the metric representation, or we can say that a matrix expression of a normal operator on Hilbert space Cn. Here are some examples of normal operators, which are as follows. The first is unitary operators such that n star is equal to n inverse. Hermitian operators, that is self-adjoint operators such that n star is equal to n. Skew Hermitian operators such that n star is equal to minus n. And the last one is positive operators such that n is equal to m into m star for some m, so n is self-adjoint. Here are some properties regarding the normal operators. Normal operators are characterized by the spectral theorem. A compact normal operator, in particular on a finite dimensional linear space, is unitarily diagonalizable. Let T be a bounded operator, then the following are equivalent. The first is T is normal, second is T star is normal, and the third is norms of Tx is equal to norms of T star x. For all x, use norms of Tx whole square minus inner product of T star into Tx comma x minus inner product of T into T star into x comma x minus norms of T star x whole square. And the last one is the self-adjoint and anti-self-adjoint part of T, that is T is equivalent to T1 plus It2, with T1 is equal to T plus T star divided by 2 and It2 is equal to T minus T star divided by 2 commute. If n is a normal operator, then n and n star have the same kernel and range. Consequently, the range of n is dense if and only if n is injective. Put in another way, the kernel of a normal operator is the orthogonal complement of its range. Thus, the kernel of the operator n raised to power k coincides with that of n for any k. Every generalized eigenvector of a normal operator is thus genuine. Lambda is an eigenvalue of a normal operator, and if and only if its complex conjugate lambda bar is an eigenvalue of n star. Eigenvectors of a normal operator corresponding to different eigenvalues are orthogonal, and it establishes orthogonal complements to its eigenspaces. This implies the usual spectral, also an infinite dimensional generalization in terms of projection valued measures. Residual spectrum of a normal operator is empty. The product of normal operators that commute is again normal. This is non-trivial and follows from the theorem which states that if n1, n1 and n2 are normal operators, and if A is bounded linear operator such that n1a is equal to a n2, then n1 star a is equal to a n2 star. The operator norm of a normal operator equals its numerical radius and spectral radius. So let's take some theorems. The first is, if T is normal, then kernel of T is equal to kernel of T star for all r greater than equal to 1. So here is a proof. Let S is equal to T star into T this is a self-adjoint linear operator, then we can see that kernel of S is equal to kernel of S raised to power R for all r greater than equal to 1. Now assume u vector belongs to kernel of SR, then we have 0 is equal to inner product of SR into SR of u bar, comma S raised to power R minus 2 u bar is equal to inner product of S raised to power R minus 1 u bar, comma S raised to power R minus 1 u vector. And we therefore know that S raised to power R minus 1 of u vector is equal to 0. Now by downward introduction on R, we can see that u bar belongs to kernel of S. Now let v bar belongs to kernel of TR. Then since SR is equal to T star raised to power R into TR, v bar belongs to kernel of TR, which is a subset of kernel of SR, which is equal to kernel of S, which is equal to kernel of T, and so kernel of T is equal to kernel of T raised to power R for all r is greater than equal to 1. Now the next theorem is, if T is normal, then adjoint of inner product of T v bar comma T w bar is equal to inner product of T star v bar comma T star w bar. So kernel of T is equal to kernel of T star. Let's see the proof. We use normality to see this. Inner product T v bar comma T w bar is equal to inner product of T star T v bar comma T w bar, which is equal to inner product of T into T star v bar comma T w bar is equal to inner product of T star v bar comma in T star w bar. Then the second part follows from the first by considering inner product of T v bar comma T v bar is equal to inner product of T star v bar comma T star v bar. In particular, this shows that the eigenvalues of T star are the conjugates of those of T and the eigenvectors are the same. Now the next theorem is, if v bar and u bar are eigenvectors for T for distinct eigenvalues, then v bar is perpendicular to u bar. So let's take the proof. Let lambda be the eigenvalue for v bar and let u be the eigenvalue for u. Then lambda of inner product of v bar comma u bar is equal to inner product of T v bar comma u bar, which is equal to inner product of v bar comma T star u bar, which is equal to inner product of v bar comma u bar into u bar mu bar into u bar, which is equal to mu into inner product of v vector comma u vector. Since lambda is not equal to mu, we only have such an equality if inner product of v comma u is equal to 0, and so v vector is perpendicular to u vector. So let's take the next theorem. If T is normal operator, then T is diagonalizable. Moreover, the eigenspaces are orthogonal. Let's have the proof. Let lambda 1 up to lambda k be eigenvalues of T. We know that we can put T into Jordan form. Then the algorithm starts with B is equal to T minus lambda I into I, and then it considers the ascending chain such that kernel of B is a subset of kernel of B square up to so on is a subset of kernel of BR and up to so on. Thus the smallest value of R such that kernel of BR is equal to kernel of BR plus 1 is the size of largest Jordan block. Thus the diagonalizability is equivalent to R is equal to 1, since then all of the Jordan blocks are 1 cross 1 blocks. Thank you everyone.